Yeah, so today I'll be presenting this double fetch bugs, like we try how to do this precisely and in a scalable way. So this is a joint work with my lab mate Chen Xun and professors Kang Jie, Michael, and Tisu. So first thing first, why do kernels do double fetch, and why do we care about this? So the double fetch all originate from this address-based separation protection, which completely separate the user space program and the kernel space. So say if you want to, this implies two things. So if you want to copy something from the kernel space to user space, you cannot directly dereference the user space pointer, for example. Just direct dereference, this is wrong. And what you should do is you should use this copy from user functions, we call it transfer functions, that specify where to copy from user space and where to the kernel space and how many bytes you want to copy. And then, so this gives us like how do we identify the fetches. So there's a second implication out of this address-based separation, which means that all the user space threads of the same program of the same processes shares the same virtual space address. So basically, every thread can have something, say, write or read to this user space address. And this means that there could be some risk condition happening. So you do something, copy something from kernel, and then at the same time, the other user space thread try to modify this value. And this is kind of the root cause of this double fetch bugs, which I'll show you later. So just now we show why do we do a single fetch, because we want to get some value from the user space to kernel space. Now, second question is why do we do double fetches? So this is a kind of example code. It's actually a simplified code in the kernel space. So the most common reason why we do double fetch is that we don't know how many bytes we're going to copy from the user space. For example, in this case, we have a very opaque user space pointer, the structure of perf event attribute. We don't know how many bytes we're going to copy to user. So what typically do is that we will prefix the format of this structure. So we say that the first 4 bytes will contain a value of how many bytes of the whole message is. So what we do is we do the first fetch, we copy the first 4 bytes into the kernel space, and then we do some sanity checks to make sure that this is not a stupid value, either stupidly large or small. And then we know that the whole message is going to be 30 bytes, and then we do the second fetch and copy the whole message into the kernel and then the function. So let's think about this. What could go wrong in this process? So basically, up until the first fetch, everything is OK. You know this 30, the first byte is 30, the size is 30. But after you're doing the second fetch, and while you're doing the sanity checks, another user space thread can override the first 4 bytes, because that is in user space, and user space thread can have access to these values. So they can override the 30 to any arbitrary large numbers. And then when you do the second fetch, you basically copy the whole message. But this time, the size, the header, or message header, or the size of the message actually changed. And later, if you do some calculation and then you want to copy the buffer back to the user space, and if you rely on the first 4 bytes to indicate its size, probably you're going to copy like 64 bytes of kernel space into user space, which is a kernel information leak. So why double fetch is quite prevalent in the kernels, or why it's kind of difficult to detect, is that there are so many reasons why, so many patterns why double fetch can happen. So what I show you just now is the size checking pattern, and there are actually more patterns in the kernel. For example, they're doing some dependency lookup or protocol signature checks. So let me show you another example. So this is how the kernels develop trying to do dependency lookup. So if you do the first fetch, you get the message header, and then you try to look up an IOC pointer based on the IOC number. And then once you get the pointer, you're going to acquire the mutex lock. And once you have the mutex locked, you're going to do a second fetch of the same header plus something else. And then you're going to do some download on the same IOC number. So what can actually go wrong is that the IOC number of the 2 different fetches can be different. So what effectively you're doing is that you are doing this do FW download on IOC number device number 2, but with the lock of device number 1 acquired. So it's up to up to the attacker to think about how they can abuse these kind of things. So another example is how do they do protocol checks or signature checks. So they basically want to early reject the message. So they copy the header and verify that the header must be, say, TLS 1.2. And then if not, it just error return. And then if you yes, then you do the second fetch and do something with the full message. But what is not expected is that after you do the first fetch and while you're doing the protocol check, this TLS 1.2 version can be changed in the header. So you can basically use any kind of TLS 1.1, 1.0, something else. So this has been a issue like brought up by Bootstrap projects in Black Hat 2013, and it's work on Windows using some virtual machine inspection techniques. So the pattern they define is that if there are going to be 2 consecutive memory accesses within a short time to the same user space address, then it's going to be a double fetch bug. So a similar technique works for the Linux, and it's recently proposed in archive. It's called decaf. So they try to do kernel fuzzing to try to maximize the code coverage, and they use a clever cache side channel to do this. So, and a more related work to us is the Usenix security last year's work. So it's also based on static analysis, and they use some lexical code matching to find the easy patterns like size checking things. So the drawback of the 3 related works is that they require manual effort. So basically what they're trying to do is that they're going to tell you there are 2 fetches, but they are not going to tell you whether these 2 fetches are actually going to cause trouble or not. So some form of manual verification is needed. However, for us, we try to minimize this manual effort as much as possible. So what do? We also do static analysis, but we also use symbolic checking to not only find that this could be double fetch. We define a model that saying that if the 2 fetches are in this shape, they are going to be double fetch bugs. And we use symbolic checking to make sure of that. And by doing so, we minimize our manual effort. So how do we define the double fetch bugs? So basically, a fetch is just a pair. It's a starting address of the user space and then how many bytes you're going to copy to kernel. And then the next thing is if you say you're going to have a double fetch bug, the 2 fetches have to have overlaps. So basically, the overlap means that you have to copy do 2 fetches, and then you either in the form of this one, so you copy somewhere in the middle, or in the form of this one, you copy the whole message header into the kernel space. And also by doing this overlap fetch, we also know that which part of the message header is overlap. For example, is it the size or the whole structure, the whole header structure in this case. So, and then knowing that there's an overlap fetch is not enough to make it a double fetch bug. So what makes it a double fetch bug is actually you have to establish some relationship between the 2 fetches. And one kind of relationship is called control dependence. What it means is that the variable has to stay in the overlap region. And in order for the variable to reach the second fetch, in order for the control flow to reach the second fetch, this variable has to satisfy some conditions. For example, in this case, in order to reach the second fetch, the header.version must be TLS 1.2 version. So therefore, we expect that after you're doing the second fetch, this property should still hold the same. Unfortunately, after you do the second fetch and until the end of this function, there's no way to ensure that this header.version, or in this case it's full.version, is still TLS 1.2. Therefore, it's kind of a violation of this control dependence, and that makes it a double fetch bug instead of just overlap fetch. So the other relationship it could be is a data dependence, which means that some value in this overlap region is used in some form of calculation, or is passed some function calls. Therefore, we expect that the same value is going to hold same after the second fetch. So, and this dependency lookup example is actually a violation of this data dependence, because once you get the first fetch, you use this IOC number to look up something. So therefore, after you do the second fetch, you expect that this IOC number is the same, but actually it's not. Therefore, it's a violation of this data dependence, and which makes it a double fetch bug. So quick recap. So to find double fetch bug, we have to have two fetches that have overlap regions, and some relation must be established between these two in this overlap region, either control dependence or data dependence. And we cannot prove that at the end of function, there's the relation is still valid after second fetch, and therefore this is the definition of the double fetch bug. So how this kind of definition help us guide us in terms of finding those things? So basically, we need to find two things. So find many double fetch pairs as many pairs as possible, and then construct the code paths that is associated with each fetch pair, and then symbolically check each of the code paths and decide whether the two fetches actually make a double fetch bug or not. So the goal, so how do we collect the fetch pairs? The goal is that we're going to statically enumerate all the possible fetches that could occur in kernel execution. So the ideal solution would be a top-down approach. So you identify all the fetches in kernels, and you construct a complete inter-procedural CFG in the kernel base, in the code base, and then you perform pairwise reachability test. Well, this is the ideal, but 2 and 3 it's not really possible right now to do in the kernel. So what we do is we use a bottom-up approach. So ideally, all the fetches we can still identify all the fetches in the kernel, but for each fetch, instead of building the whole kernel CFG, we start with the function it resides in and then scan through its reaching definitions to find the fetches or fetch involved functions. So a quick, some details is like, so you start from a fetch, which is copied from user function, and then you go upward to find all these reaching instructions. And in the first case, you find a fetch, which is good. You find a fetch pair. Now you can start, you find a path, and then you can start to symbolically check whether it's a double fetch or not. And then in the second case, you find a fetch involved function. So although this is not a copy from user or something function, but somewhere inside the function, there's a copy from user, and you can just inline the function over there and then redo the whole thing, and you will find a fetch pair. And then in the third case, there's no other fetches, so this is a single fetch. So don't worry about this. So we finished the first part on how to collect the double fetch pairs. Now the second part is given each code execution path, whether do you remember the conditions we say whether there is a control flow dependency and whether or data flow dependency and whether this relation still hold after the first fetch. So this is what we do for this symbolic checking. So as I said, we are going to prove that the relation still holds or doesn't hold. So how do we do that? Let me walk you through with this example. So it's the same code we show you just now. So upon entering this function, we're going to know some immediate facts. Like there are going to be two arguments and then function parameters. And then the first parameter points to a user space memory, and the second parameter points to a kernel space memory. So you have some like basic understanding of the memory layouts. And then during the first fetch, you will collect the fetch information, which is notated in fetch f1. So basically, it tells you that it starts from the first parameter plus 4, and give the starting address is the first parameter plus 4, and then the size is 4. Basically, you fetch 4 bytes from the user. And then you do some sanity checks, basically translated to some symbolic execution. Is that if you're going to reach the second fetch, you expect that this size variable, which is represented by $2, have to satisfy certain conditions. And now you reach the second fetch pair, you do the same thing, and then you derive the A and S, which is the starting address and the size of the whole fetch. And now, once you reach the end of the function, you are going to do two checks. The first check is that whether there is an overlapped fetch, which means that you are going to see that whether the f1.a and f1.s and f2.a, f2.s satisfy a certain constraint. I mean, if you satisfy, there is an overlap fetch. And in this case, it turns out that there is an overlap fetch, and the region is annotated with 0, 4, and 7, which means that it's the user space function pointing to by UATTR from byte 4 to byte 7. These are the overlap region. And then the next thing you're going to prove is that, or disprove, is that whether these two fetches from the first one and the second one are the same. And it turns out that there's no constraint that in this function to show that these two fetches have to be the same. And therefore, we conclude that this is a double fetch bug because there's a data dependency established, but we cannot prove that the thing fetched across the two fetches are the same. So we actually have a more complicated example in the paper, which shows you how we do loop unrolling and some simple pointer resolving. So if you're interested, you can feel free to refer to our paper on this. So findings. So we find 24 bugs in the kernel in total. So 23 is in Linux and 1 in FreeBSD. So 9 bugs have fixed with the patch we provided, and 4 bugs are acknowledged, but the patch is not very easy to provide, and we are still working on a fix. And there are 9 bugs pending for reviews, and there are 2 bugs marked as won't fix, which one of the bug is actually a double fetch bug confirmed, but the developer thinks that there is no serious security issues in it, so they say that let's just ignore it for now. And the other bug is a assumption we made, which is not quite wrong or quite right in the process. So basically, we argue that in the whole function, there's the two fetches happens in the same function, but it turns out that there could be cases that when you exit the function, you still have the information of the first fetch, and therefore you can still do some validation outside this function, so to make sure that the two fetches have the same value. But this is not very common in the kernel space. We only have one such case, and this is what marked as won't fix as well. So how do we mitigate these bugs? So the basic idea is to reassure that this control dependence and data dependence still hold after the two fetches, so which means atomicity in the kernel space memory accesses. So based on our experience, we have 4 generic patterns in patching them. So the first one is you just override the second fetch. So I don't care what you fetch in the second fetch. I just override the value with what I get in the first fetch, and we're good to go. So the second way is I'm going to check whether you modify something while after the first fetch. And if I detect you modify something, I'm going to abort. So the third thing is like, let's do incremental fetches instead of overlap fetches. So we fetch a first region, and then we fetch an offset of that. Basically the rest of the message into the kernel. And this requires some refactoring of the code, obviously. And then the last part is let's don't do double fetch. Let's just do a single large fetch, which we do all this magic inside a single fetch. And this is a very complicated and case-by-case thing. So this strategy is usually requires a lot of code modifications. So, and unfortunately, we don't find a generic way of patching all these double fetch bugs. Some requires heavy refactoring of the code, or even redesigning the interface and structures. So, and recently, Decaf has provided a promising solution to use TLS-based technique to ensure the user space memory, the atomicity among them. So if you're interested, feel free to check the paper. So some limitations, we could not analyze anything not compatible with LLVM. And there are some execution path constructions limitations. For example, we couldn't handle a path that has too many branches, and we only do loop unrolling once. So, and symbolic checking, we ignore those inline assemblies. But fortunately, there are not many in the double fetch cases. And we may have some imprecise pointer to memory object mapping things. So in conclusion, we have precise, and we find that if you have a precise and formal modeling of this bug, it makes things very easy to write the tool to detect it. And we find that there could be more applications beyond the kernel, for example, the hypervisors or trusted computing bases. As long as there's a clear separation of the privileges, and you can find the functions of how to access like upper or lower privilege regions. And then we think that logic bugs compared with these memory safety bugs are on the rise. So we hope that there will be more formal modeling of the bugs and formal like systematic tool to find them. So we'll open source the code in the link, so feel free to check back. And with that, I conclude the presentation. Thank you.
Yes, so we have time for one quick question because we are already running out of time.
Hello, Chang from Temple University.
Hi.
I'm interested in some details about the symbolic executor. So what's the entry point for your symbolic execution? It's the containing system call or the containing?
Yeah, good question. So yeah, the entry point of the symbolic execution is the containing function, which is the nearest function that contains both fetches.
So which means that you will lose a lot of constraint information?
Well, technically, you could lose a few. You could lose a few information, but they are actually not very relevant because we will also do some slicing out of this execution. So we're not going to execute simulate all the instructions. We're only going to execute the instructions that could affect the starting address and the size of the whole fetch. And then for that, we think it's good enough to just start from the function that contains it. And we assume that the function arguments can have point to any user space memory, and we assume that they are not going to overlap. We have some of the details in the paper, so feel free to check it. And yeah, so we feel that this modeling is good enough to reconstruct the whole case.
Okay, very nice work. Thank you.
Thank you.
Okay, so let's thank Meng again.
Thank you.